All right. So yesterday we were talking about kind of the first of many in terms of taking this framework that we have, this kind of general notion of what is a function, and applying a more specific example to that framework. So yesterday looking at kind of our most basic of functions, this was our linear function. Today what we're going to be doing is we are going to be expanding on what we were looking at yesterday, as well as taking some of the ideas that are very important to a linear function and seeing how well do they generalize when they're not just talking about lines, when we're talking about maybe some slightly more robust, interesting dynamic functions. The focus of today is ultimately going to be the slope of various functions, and kind of seeing what the slope does, how it interacts, some kind of specific instances of that, and then again, kind of taking that and expanding it. So where we're going to kick off is with a brief discussion of parallel lines and perpendicular lines. So if not a review from Algebra 2, hopefully a review from geometry. What does it mean for two lines to be parallel? Okay, they never intersect. I think that that is certainly a great place to start. So maybe we say two lines that do not intersect. And if I have two lines that do not intersect, what must be true about both of those lines? What do we know about two lines that don't intersect? Okay, they are always equidistant. That notion is a little bit weird because we can kind of like take the distance to a whole bunch of different points, but we might say that the difference in their heights never changes, right? That we have this constant kind of gap between the two that never gets smaller. Let's say maybe take that and turn that into something that is a little bit more mathematical. If you and someone else are, we'll say, like 10 meters apart, 10 yards apart, whatever, on the road, and you are going the same speed, does the distance between you ever change? No, you're effectively kind of traveling in tandem, almost like these two parallel lines. What is the way that we can kind of take this notion of speed and translate it into what we are doing with lines? What about the linear function? They're slopes. The slopes kind of give us this sense of how quickly, as x increases, does our line move. We kind of can think of steeper slopes as meaning that we are moving more quickly, kind of more slumped slopes, flatter slopes, as being moving more slowly. And so what can we say about the slopes of two parallel lines? That they are the same. If they are moving at the same speed, then the slopes are equal. Okay. What about perpendicular lines? Parallel lines, two lines that never intersect. How do we define lines that are perpendicular with one another? So they do intersect, but there are a lot of different ways that we can intersect, and perpendicular do it in a bit of a special way. So what's special about the way that perpendicular lines intersect? They form 90-degree angles. Fantastic. So maybe something like this. See how well that? Yeah, it looks close enough. Where the angle between our two lines is going to be 90 degrees. So again,
perpendicular lines, maybe we say lines that intersect at a 90-degree angle. Now, I don't think you guys have really ever probably seen why we care about perpendicular lines all that much. Maybe a little bit in geometry. You can see that there are some kind of geometric properties that rely on perpendicular lines. But ultimately, this whole notion of being perpendicular and that being important stems from kind of how vectors work. There's some very interesting things to explore when we have vectors that are perpendicular, that even has a special name. We describe those as orthogonal. That is something that we're not even really going to get into when we cover vectors, but just kind of tucking away. If you ever take a linear algebra class, you will see that it's very, very good to have these kind of lines that are perpendicular. All right. And just to kind of match what we have done with parallel, if we have parallel lines where the slopes are equal, what can we say about the slopes of perpendicular lines? Okay, more specifically. Opposite in what way? What do we mean by opposite? Okay, so fraction word for that would be like reciprocals, but are they just reciprocals? No, they're reciprocals and also they swap positive negative. Right? Oftentimes this is described as opposite reciprocals. So opposite being one piece, that kind of reverse, or that reciprocal piece being another. These slopes are opposite reciprocals, which is just to say, if the slope of my blue line is equal to 2, what is the slope of my purple line here going to be equal to? -2? -1/2. Again, why this happens is probably not something that you've explored because you haven't worked with vectors. There are some very interesting kind of geometry things that get us this relationship. A lot of interesting vector math that we could do that would give us that relationship, none of which we will explore even when we cover vectors. All right. So let's take a look here at example 1 from the long problem set. In this case, we are trying to compare two sets of lines, figure out if what we are looking at are a pair of parallel lines, perpendicular lines, or neither. All right. So looking at A, we are given the set of lines here. We haven't really looked at lines in this particular form all that much. We looked at lines in our y equals mx plus b form, that kind of slope-intercept form. We've looked at some lines in our point-slope form. This is the third representation of lines. This is called like standard form or general form for lines. It's very, very good at telling you or helping you figure out the x and y intercepts. It's not really that good at anything else, which is why generally we kind of like to solve our lines for a slightly more useful format. The main problem being that if we are given lines in standard form like this, it is not readily apparent what the slopes of those lines are going to be. We have to do a little bit of work in order to figure that out. So what kind of work do I have to do to this in order to figure out what the slopes of these lines are going to be? How would you find the slopes for, say, what we have for example A? Solve for y. If we solve for y, and this is in fact a line, we'll probably end up with something that's like y equals mx plus b, and then we will be able to very clearly see what the slope is. All right, solving for y, when we have a two-variable equation here, solving for one of them, you kind of treat the other one like it's just a number. So we are going to try to isolate y, first subtracting 4x from both sides. I get that negative 7y is equal to, I'm going to write this as negative 4x plus 10. You could also write this as 10 minus 4x, but I'm trying to show you that this is in fact a y equals mx plus b kind of setup. So just leaving it like this. And then finally, last step, solving for y, I divide both sides by negative 7. And I get that y is equal to negative 4 divided by negative 7. I'm going to get positive 4 over 7x. Positive 10 divided by negative 7, I get negative 10 over 7. And so what is the slope of this first line here? 4 over 7. That M right there. All right. Second line, exact same thing. Subtract 7x from both sides, divide by 4. I get that 4y equals negative 7x plus 1. And I get that y is equal to negative 7 over 4x plus 1 over 4. What is our slope here? Negative 7 over 4. And so what can we conclude about these two lines? Are we looking at parallel lines, perpendicular lines, or some other, or neither of those two kind of designations? These are definitely perpendicular. Fantastic. Opposite reciprocals. Questions with example A here? All right, we're going to take, we'll say 5-10 minutes-ish. Work through B and C. Trying to figure out are what we were looking at parallel lines, perpendicular lines, or so notice here how one of them is negative, one of them is positive, and how one of them is like the flipped upside down version. If they're the same, then they would be parallel. If they're this flipped upside down version, and one's negative, one's not, then they're not. So can we simplify? Yes. So try simplifying these other nine and then see if they look. so much easier. This is good. I think you the bars on top. Or are you saying like what the slope would be?
That's using this.
Yeah, you flipped it upside down. Those 4 over 2, so but ultimately, your conclusion is being the same thing, right? Are they the same? Do the slopes? No, but are they opposite reciprocals? Are they? Those ones that flipped up. So they are. -1 minus 3. I get -1. Okay. So subtracting, not just 6, we're going to subtract that whole 6x term. Swing it over to the other side. No. So think of the semicolon as like this is one equation, this is the other equation. Okay, so we got 6 over 9 here, and then we got, okay. See if you can simplify that 6 over 9. That looks a lot easier. Yeah. Yes. Yeah, because all we're trying to really do is compare slopes. So we don't need to know anything about the line really, other than the slope to this. Okay. Okay, I would do this algebraically rather than by graphing, just because it's kind of hard to be super precise when we are graphing. Yeah, so try solving these to see, what we're trying to do is we're trying to compare their slopes. So try to get this into that y equals mx plus b form so that we can like look at how those slopes kind of compare with one another. Basically, you're solving this for y, and then you're solving this for y. For c. Okay, for C, you're going to want to still compare the slopes. So you're looking at how can I write the slopes. Yeah. Just make sure that your points line up. So if you're using 3 as your first y value, you can use 2 as your first x value. So instead of 4 minus 2, it would be 2 minus 1.
Okay.
Yeah, but otherwise that looks hard. -1 minus, what's the other y value here? Yeah, perfect. This looks good. Yeah, we go there. Conclusion would be that it's perpendicular, but the math looks good.
Yeah,
8 minus 6. No, that's just a little thing. The setup is the important thing. That's the how do we find the slopes for 2 points? Yeah, that's the one. So change in y over change in x, y2 minus y1 over x to x. Perfect. All right, fantastic. Let us go over these. We're not going to work them all out all the way through, but I do just want to get the slopes. So for B, what was the slope that we got for this first line here? What did we say? 2 over 3? 2 divided by 3? Fantastic. And then what was the slope for the second line? -3 over 2, or -3/2. And so what is our conclusion here? That these are perpendicular. Very good. Awesome. For C, 2 points, figuring out the slope between those 2 points. We have a formula for that. What was the first slope that we got? -2 over 1. And what was the second slope that we got? Just 1. And so are these the same? Are they opposite reciprocals of one another? No. And so this is not parallel nor perpendicular. They are just 2 regular old lines. So this is the y2 minus y1 over x2 minus x1. So how much has our y changed, or how much has our x changed? All right, taking a look at example 2 here. We're being asked to write an equation for a line that is perpendicular to the line that we are given, that passes through a particular point. Now, this might feel a little bit complicated, especially if we were to try to get this into that y equals mx plus b form. That could certainly be very annoying, but we don't need to do that. All we need is a point and a slope, and we can then just write this in point-slope form and be done. So looking at A, if the line that we are given is 3x minus 1, what is going to be that perpendicular slope to what we see here? So M perpendicular is going to be, well, the original slope is 3, so what's the perpendicular slope going to be? -1 over 3. And that's all the information we need. This is y minus, well, y1 in this case is just 9, equal to our slope times x minus, in this case our x1 is 4. And sure, we could try to solve this for y equals mx plus b, but why would we do that? No point. Let's just leave it like this. All right, exact same thing for B. If my slope is -2, what is my perpendicular slope going to look like? -1/2? +1/2, perfect. And that's all the information I need. I have the slope, I have a point. This is now y minus 1 equal to 1/2 times x. You could write this as x plus 4, just so we're really clear as to what formula I'm plugging it into. I'm going to write this as x minus -4. But do just kind of make note that that would simplify to x plus 4. All right. Any questions here with example 1 or 2? All right. All of this is very line specific, right? Talking about parallel, perpendicular lines, but very, very limited to kind of make these conversations. In fact, when we talk about slope in general, it's very, very limited to discussion about lines. What we're going to do now is do our best to kind of take this idea of lines and their slopes and see, can we come up with something that is maybe a little bit suitable for not just lines, but any function that we could come up with. Right. So we could maybe imagine a scenario in which, let's say we want to track how long, the speed at which I go from home to work. And we could maybe plot my position, my distance from work with respect to the amount of time that it takes to get there. And we could imagine that, I start out pretty far away. So if this is our axis, that's like distance from work. And this is the time. I start out pretty far away. And maybe driving through my neighborhood, I have to go a little bit slow. But eventually I get on the highway so I can move faster. But then all of a sudden I remember, oh, I forgot my laptop back at home. So I have to turn around and go back home and grab my laptop. And then I have to really speed to get in at a somewhat reasonable time before finally arriving at school. Assume like plowing through like all of the parking lot and all that fun stuff. Ideally, we would have like a little bit of a gradual descent here, but such is life. A very, very messy function that is not really going to be well modeled by this notion of, at the very least, not how long. Big difference between what we're looking at here and what we look at with a line. Think of living on a line is just traveling a single speed all the time, all throughout the course of the line. It is a constant slope. It is a constant, how we describe it, rate of change. Whereas a lot of our functions are sometimes growing really quickly and sometimes they're switched from growing to decaying. Sometimes they're not moving at all. Who even knows? And so generalizing this maybe feels like it wouldn't work super well. And ultimately, to kind of really nail this question of how can we describe the rate of change for our function, how can we get a really good picture of how this function is kind of evolving as we move along our x, you take a calculus class. This is really where in fact, that is like the central question that you investigate with calculus, which is how can I really, really precisely describe the rate at which we see change here? We are not in a calculus class. We do not need to have that good of a set of descriptors. And so what we're going to do is we're going to kind of take advantage of something. And that is just how averages work. Because on average, if I start at a start point and end at an end point, it doesn't matter all the craziness that I've passed through to get there. Ultimately, all that matters is the amount of time per the distance traveled per the amount of time. For this trajectory to work, I might as well have started from my start point and just gone straight there, but at a different speed to arrive at the same conclusion. In other words, we are going to ignore all of the complicated garbage that is going on with our functions. We're just going to pretend that it's a line. Which means that when we are taking this average rate of change, it is no different than taking this. As far as definitions go, average rate of change, we're going to just describe this as the average slope over an interval. Now, this idea of over an interval is very important. For lines, it doesn't matter what interval you pick, the slope is always going to be the same. But if we look at this crazy trip to work, we notice that taking the slope of what's going on, say, like here, is going to get me a very different slope than if I'm looking at what's going on over here. Right? So where we are becomes a little bit more important here, whereas with lines, we don't really care. So alongside this idea of slope, we also now have this added idea of an interval. But that's actually entirely fine because we already needed a start point and a stop point to figure out slope. What is our formula for slope that we have been using, that we talked about yesterday? That is slope-intercept form, but what is the formula for slope? y2 minus y1 over x2 minus x1, where y1 is where I end. In fact, the point x2, y2 is the point where I end, and the point x1, y1 is where everything starts. Okay, we're going to spruce this up a little bit. Not going to change the meaning of anything, but a little bit unhappy with the fact that when we're talking about y, it very specifically refers to a graph. The y is the height of a graph. We can apply this idea to more than just graphs, though. And so just to make this a little bit more palatable, to make it a little bit more consistent with what we have been talking about, instead of y2, which is the output of my function at x2, I'm going to say that we are looking at f of x2. Have I changed anything? No, y2 and f of x2 are basically the same thing. This just makes it a little bit more consistent with my function notation. Similarly, instead of y1, we're looking at f of x1, still over our change in x here, x2 minus x1. But ultimately, it's the same thing. It's just still y2 minus y1 over x2 minus x1. How much has our output changed per change in our x? All right. Let us take a look at example 3 here. Got about 10 minutes left. We'll come back to A. We'll have a lot of time to practice ones like A ends up not being bad. Your x2, your x1 and your x2 are just your start and stop of your interval. To find the y2 and the y1, you plug it in, you evaluate, blah, 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 you see what you get. Not too bad. We're going to look at B. B's a little bit worse. And I want us to have worked through B together before I send you off and let you attempt it on your own, because it's a little bit rough. So for B, we are told that A of t is equal to 1 over t plus 4. We are asked to find the average rate of change over the interval, starting at 9, ending at 9 plus h. Okay, couple of weird things. You guys may have done stuff with average rate of change before. This may be your first time encountering something like this 9 plus h stuff. So what is the plus h? What is that telling us? Think of the plus h as just telling us how much you're sliding to the right. If we slide 3 spaces to the right, then we're looking at the average rate of change between 9 and 12. If we slide 1 space to the right, we're looking at the average rate of change between 9 and 10. If we slide half a step to the right, between 9 and 9.5, and that h is just basically saying that's the amount that we are sliding to the right. We start at 9, and so our second input would be 9, and however much we have moved from 9. Feels a little bit redundant, but we'll see kind of in the formula that is in fact how that is going to work out. Think of that h as just like the change in x. How much has our x changed? If we were pursuing calculus, the goal would be to make this h as small as possible to get a really, really good idea of what's happening exactly at 9. This is not calculus. We are not going to be doing that. All right. So we are trying to find average rate of change. That is just slope. The average rate of change in this case equal to the change in our y's. In this case, that is a of 9 plus h minus a of 9 divided by the changes in our x's. That is 9 plus h minus 9. Right? To be very, 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 very clear, The interval that we are given is a bunch of x values. This 9 here is x1. This 9 plus h is that second x value, x sub 2. Right? Okay. A of 9 plus, actually before that, thing to note in the denominator, what do I have that happens here? It makes things a little bit nicer. 9's cancel. Fantastic. 9 minus 9 is in fact 0. These go away, and we're left with just h, which is good. The denominator of our slope is the change in x, and I just said that h is also the change in x. Bam. H is what's left in the denominator. All right. Let's figure out what's going on with a of 9 plus h. What is this asking me to do? Is this asking me to distribute here, a of 9 plus h? We're substituting 9 plus h into t, right? So I feel like we're really, really good at doing the substitution when the function is like f or g or h. In this case, the function is just a, right? So remember, not distributing, we are substituting everywhere we see a t, replacing it with a 9 plus h. Fantastic. What is that going to give us? That is going to be 1 over 9 plus h plus 4, where, well, really, 9 plus 4, that's going to give us 1 over 13 plus h. All right, same thing with a of 9. Plugging in 9 for t, I get 1 over 9 plus 4, that is 1 over 13. And so what is my average rate of change? Well, this is going to be 1 over our a of 9 plus h. That's 1 over 13 plus h minus 1 over 13, all divided by h. That's our slope. Okay. So the bad news is that I said that I was totally fine with you leaving your answers unsimplified, except there's like one situation where you're going to need to simplify things, and we'll talk about it. Thank you. We'll talk about it later when it comes up, and it's a little nasty, and sorry about that. Welcome. This is the nasty simplification process that we are going to have to do. The idea, basic here, is that I want you to get practice doing this while there are still numbers. I want you to become really, really, really good at dealing with fractions before it all turns into cosines and sines. Because ultimately, that is where we will be in quarter 2. Is this same problem, but no numbers left, just cosines and sines. All right. So let's talk about simplifying what we have here. Not packing up yet. We still have 4 minutes of class. This is one of the hardest problems that we are going to do for a while. Let's make sure that we are focused. What do I mean by simplify? What do I want to see here? I don't like having these nasty like fractions that are in my numerator. I want to get a really simple numerator over denominator. The way we are going to do that, our goal, is we are going to build a fraction tower of a over b all over c over d, a massive stack of fractions where once we have this, we can write this as a over b times d over c, multiply by that reciprocal, and simplify down into just number over number. Okay, denominator looks okay, but we do need to clean up the numerator. I am trying to subtract 2 fractions that have different denominators. Am I allowed to do that? No. What do I need to do? Am I allowed to add something directly into the denominator? No. It's going to be a little bit trickier than that. What do I need to do? What do I need to make sure is true about my denominators? I need common denominators. They need to match. The easiest way to get a common denominator when I'm adding or subtracting two fractions is to just multiply them together. All right? So to match these denominators, I need to take 1 over 13 and multiply that denominator by 13 plus h. If I do it to the denominator, where else do I need to do it? I also need to do it to the numerator. 13 plus h. Over here, what am I going to need to multiply by? 13 over 13. If I'm matching it, have to match. All right. Let's do some multiplication here. This is the part where we don't need to simplify. Fantastic. We get 13 over 13 times 13 plus h minus 13 plus h over 13 times 13 plus h, all divided by h. Good news. In our numerator, we now have matching denominators. We can now subtract our fractions. Problem here, not really a problem, just a thing to note, is that this negative is hitting the 13 and what else? The h. Both the 13 is getting subtracted and the h is getting subtracted. We do out the subtraction. 13 minus h. This is going to give us negative h over 13 times 13 plus h, all divided by h. And for that last piece of our tower, I'm going to write this h as h over 1, just so it's really clear what I am doing. This is my a over b over c over d. One final step, we are taking that fraction in our denominator, multiplying by the reciprocal. Rather than dividing by h over 1, we are multiplying by 1 over h. That is going to give us negative h over 13 times 13 plus h times 1 over h. What is going to happen with my h's? They are going to cancel, and we are going to end up with negative 1 over 13 times 13 plus h. And that is our slope. All right, I know I went through it fast. That was so that I would have a recording of the full problem. You'll have a time to practice with 1.4. 1.4 piece of the classwork done by tomorrow at the end of class for that extra point. 1.4, 1.5. We'll have the homework and quiz, or the classwork and quiz, sorry, due Sunday and then Monday respectively.
Why would you not just multiply the one that's missing?
The h. So if it was 13 times h, you definitely would do that. So if it was 13 and 13h, the problem is because of it's the addition. It's not divisible by h. So it's because it's the addition instead of the multiple. But if it were 13h, you're totally right. That's 100% what you say.
Sir, yeah. I got a quick question.
Yes.
Part of the reason why I'm so confused is, am I supposed to know what some of these equations mean? It's not that I'm confused that I can't figure out because I'm missing a few pieces. I don't know what any of that means. I feel like I should. It looks like someone's trying to math major's head into
So the things that I would say, so a lot of this is a high-level application of formulas that I would say that we should know, but all of it is stuff that also, I'm not assuming that anyone comes in here knowing anything. This is all slope. So everything that we just did was an application of our slope.
Yeah, that's one thing I remember.
Yeah, so we're taking that.
Stuff that I know that.
Yeah, so we're taking this and we're just doing high-level plugins and substitutions with it.
I don't really know what this means. And on the other screen, like the stuff we did a little bit earlier, I just.
Okay, so what I would recommend then is Khan Academy is really good. Yeah, Khan Academy is really good. And then I would say also to that end, double check the lectures and see, can you like